Imagine two coins. You flip one here on Earth and it lands heads. At the exact same moment, a billion light years away, the other one lands tails. No one planned that. Nothing connected them. No signal, no wire, no message traveling between them. They just knew. Like two strangers on opposite ends of the universe who somehow never stopped being the same person. But because the universe, at its most fundamental level, refuses to let them be strangers. Albert Einstein heard about this, and it bothered him deeply. He called this spooky, and he spent the last 30 years of his life trying to prove it couldn't be possible. But he was wrong. And the experiment that proved him wrong is one of the most beautiful, most important things ever done in the history of science. By the end of this video, you will understand something that took humanity 80 years to prove. We're going to talk about quantum entanglement. We will follow the greatest minds in physics, Einstein, Bohr, Bell, Aspect, through one of the most dramatic intellectual battles in human history. We will watch a theorem get born in a canteen at CERN that should not have been possible. We will watch an experiment violate the laws of classical reality with statistical significance so overwhelming it makes mathematicians nervous. And at the end, we're going to ask what that actually means about the universe you are living in right now. Let's go. Princeton, 1935. Albert Einstein is arguably the most famous scientist alive, and he is furious. Not at a person, not at a government, at quantum mechanics itself. See, quantum mechanics had been born in the 1920s, and it was spectacularly successful. It predicted how atoms behave, how light interacts with matter. It was, and still is, the most accurate physical theory ever constructed by human beings. But Einstein couldn't shake a feeling. Something about it felt wrong. He and two colleagues, Boris Podolsky and Nathan Rosen, published a paper in 1935. 3 initials, 3 men, one enormous grenade thrown at the foundations of physics, EPR. Their argument was elegant, almost surgical. They said, look, suppose 2 particles interact and then fly apart to opposite ends of the galaxy. Quantum mechanics says, before you measure them, neither particle has a definite spin. They exist in superposition, a kind of fog. But the moment you measure particle A, you instantly know the state of particle B, no matter how far away it is. No delay, no signal, instantaneous. And here is Einstein's problem with that. He believed deeply in 2 things. Call them the twin pillars of classical reality. First, realism. Physical properties exist whether or not you look at them. The moon is there even if nobody is watching. Second, locality. Nothing, no signal, no information, travels faster than light. Special relativity makes this non-negotiable. Together, these form what we call local realism. It was the bedrock, the floor, the thing that made the universe make sense. And quantum mechanics, at least as it was being interpreted, was drilling holes straight through that floor. Einstein's conclusion? Quantum mechanics must be incomplete. There must be hidden variables, tiny undiscovered properties that predetermine the measurement outcomes. The particles know their spins in advance, like sealed envelopes. We just can't read the envelopes yet, but the information is there, local, real, safe. He called the alternative, entanglement across cosmic distances, spooky action at a distance. And for 29 years, nobody could prove him wrong, because nobody knew how to test it. It was philosophy dressed as physics. two interpretations of the same math completely irreconcilable with no experiment to tell them apart, until a man sat down in a canteen in Geneva and rewrote the rules of the game. John Stuart Bell was a particle physicist, a practical man, an Irishman working at CERN on accelerator design, not on the philosophy of reality. This was not his job. But Bell had read the EPR paper, and he had a feeling, the kind physicists get that keeps them up at night, that the debate wasn't just philosophy, that somewhere buried in the mathematics was a way to test it. In 1964, he found it. Bell's insight was breathtaking in its simplicity. He said, if Einstein is right, if hidden variables are real, then the correlations between distant particles must obey certain mathematical limits, no matter what. Even if we don't know what the hidden variables are, even if they're arbitrarily complicated, any local realistic theory operating within the laws of cause and effect and speed of light limits must keep its correlations below a specific ceiling. He wrote that ceiling as an inequality. Today, it's called the CHSH Inequality, named for Clauser, Horn, Shimoni, and Holt, who refined it into a testable form. The math is elegant. You take two particles, send them to two detectors, call them Alice and Bob, each randomly choosing from different measurement angles. You calculate a correlation number, S. And Bell proved if local realism is true, S must be less than or equal to 2. That's the ceiling. That is the hard mathematical wall that any classical, realistic local universe is forbidden to breach. No loopholes, no exceptions. S less than or equal to 2, or Einstein was right all along. Then Bell computed what quantum mechanics predicts for the same experiment. Quantum mechanics predicts S equals 2 times the square root of 2, 2.828. That number, 2.828, doesn't just violate the inequality, it smashes through it. It says the universe is more correlated than any locally realistic explanation can ever account for. Not slightly more correlated, impossibly more correlated. But a prediction on paper is not a fact in the universe. The first test came in 1972. John Clauser, using calcium atoms emitting entangled photons, ran the experiment. The results violated Bell's inequality. Einstein was wrong. But the loopholes. Two devastating experimental imperfections called the detection loophole and the locality loophole left tiny mathematical escape routes where a stubborn local realist could dig in and survive. Alain Aspect in 1982 came closer. He switched his detector angles while the photons were in flight using acoustic optic modulators, slamming shut the locality loophole. The violation held, but detection efficiency remained imperfect. For decades, it was a perfect catch-22. Photons, easy to separate, hard to detect perfectly. Massive particles, easy to detect, hard to separate without corrupting entanglement. And then, 2015, Delft University, the Netherlands. A team led by Ronald Hansen used electron spins trapped in diamond, tiny crystal defects called nitrogen vacancy centers, separated by 1.3 kilometers. Diamond holds entanglement magnificently. Detection efficiency was near perfect. The measurement events were space-like separated. Literally, no signal traveling at the speed of light could have connected them. Every loophole, simultaneously, slammed shut. The result? S equals 2.42. 2.42 is greater than 2. Local realism, the bedrock of Einstein's universe, was not just challenged, it was eliminated with a statistical confidence so overwhelming the probability of it being a fluke is less than 1 in a billion billion billion. And now the question is, what does that actually mean? And I promise you, the answer is weirder than you think. Here is the fork in the road. Bell's theorem proves this. The universe cannot be both local and realistic. One of these pillars or both must fall. You can choose to abandon locality, accept that entangled particles are connected by some kind of influence that transcends space, that when Alice measures her particle in Geneva, something genuinely, physically determines Bob's result in Tokyo at the same instant. This is Bohmian mechanics, pilot wave theory, deeply deterministic, deeply real, but requiring a universe with invisible, faster-than-light connections underneath the surface. Or you can abandon realism, accept that the particles simply do not have definite properties before measurement, that reality doesn't exist independently of the act of looking, that the moon, on the quantum level, genuinely isn't there until something looks. Neither option is comfortable. But notice something extraordinary. Bell's violation doesn't just survive as a statistical argument. The three-particle GHZ state, formulated by Greenberger, Horn, and Zeilinger, delivers something even more devastating: a logical contradiction. A single algebraic proof that local realism demands an outcome of +1 for a specific measurement, while quantum mechanics demands exactly -1. Not a matter of statistics, but of pure logic, provable in a single run of a thought experiment. The universe, it turns out, is playing by rules that cannot even be described in classical terms. But here's the part that saves us from madness: the no communication theorem. Yes, entanglement is real. Yes, the correlations are instantaneous. But, and this is one of the most beautiful mathematical results in all of physics, you cannot use entanglement to send information. Not a single bit, not a 1 or a 0. Why? Because when Bob looks at his particle, he sees a random result. He has no way of knowing from his random result alone whether Alice measured hers or didn't, whether she got spin up or spin down, until she calls him on a regular old telephone. The non-local correlation only becomes visible when you compare notes through normal, light-speed-limited classical communication. The math is airtight. Bob's reduced density matrix, the equation describing everything Bob can observe, is completely unchanged by anything Alice does. The universe is correlated across space, but it encrypts that correlation in a way that makes it illegible unless you already have the classical key. Einstein's relativity is safe. Causality is preserved. The cosmic speed limit stands. And then there is the question that haunts physicists to this day: Tsirelson's bound. If quantum mechanics allows non-locality, why doesn't it allow more? Theorists have shown you can write hypothetical superquantum boxes that respect the no communication theorem perfectly, but push those correlations all the way to S equals 4, the maximum algebraically possible. And yet, the universe stops at 2.828. Not at 3, not at 3.9, exactly at 2 times the square root of 2. Why? What principle is the universe obeying that is stricter than relativity itself? Why is it precisely non-local enough to be quantum, but not so non-local that information theory falls apart? We don't fully know. And that question is one of the most beautiful open wounds in modern physics. For most of its history, entanglement was pure philosophy, a conceptual weapon in a war between Bohr and Einstein, a test of the universe's deepest rules with no application beyond the laboratory. And then, in 1991, a physicist named Arthur Eckert published a paper that changed everything. Eckert looked at Bell's inequality, the same mathematical tool used to test the foundations of reality, and said, what if we used it as a security system? His protocol is called E91. Two parties, Alice and Bob, receive entangled photon pairs from a central source. They randomly choose measurement angles, measure their photons, and compare results over a public channel. For the subset where they chose the same angles, they extract a perfectly correlated, perfectly random cryptographic key that no one else has. But here is the genius. They use the other subset, the pairs measured at different angles, to compute the CHSH statistic. If S is close to 2.828, the channel is clean. The photons are genuinely entangled. No eavesdropper has touched them. Because here's what happens the moment any eavesdropper, intercepts even a single photon. She collapses its superposition. The entanglement is destroyed. The CHSH value plummets toward 2. Alice and Bob see it immediately. Eve is caught, not by a firewall or an encryption algorithm, but by quantum mechanics itself, by the fundamental structure of reality. This is not theoretical security. This is security guaranteed by the laws of physics. In 2017, China's Mesius satellite, the world's first quantum science satellite, beamed entangled photon pairs through the vacuum of space to 2 ground stations over 1,000 kilometers apart and established a provably secure quantum key at a rate of over a kilobit per second. The era of satellite quantum cryptography had begun. And entanglement's reach goes even further than cryptography. Without entanglement, quantum computers are just very expensive classical computers. The superposition of qubits alone is not enough. It is their entanglement, the holistic, non-separable, correlated quantum state spanning all qubits simultaneously, that generates the exponential computational advantage we are beginning to exploit. But the deepest, most philosophically unsettling application of entanglement research may be the 2019 Wigner's friend experiment. Imagine a lab inside a lab. Wigner stands outside, and inside, his friend makes a quantum measurement and records a definite result, a fact. From Wigner's perspective outside the sealed lab, the entire interior, friend, particle, measurement device, recorded result, remains in superposition until he opens the door. Whose reality is correct? In 2019, researchers built a photonic version of this with 6 entangled photons. They violated the associated Bell-type inequality by 5 standard deviations, with locality and free choice assumed to hold. The mathematical conclusion is unavoidable. If locality and free choice are real, then the facts established by the inner observers and the outer observers are genuinely contradictory. Not in an epistemological sense, in a physical, mathematical sense. There may be no observer-independent reality at the quantum level. The universe doesn't just play dice, as Einstein feared. It may play a game where the dice don't have faces until someone looks. And speaking of someone looking, the most radical defenders of classical reality have one last card left to play. And it's the strangest one of all. The most desperate move left for anyone who wants to save Einstein's universe, local, real, deterministic, is called superdeterminism. The argument goes like this. Every Bell test assumes the experimenters have free choice, that the random number generators choosing detector angles are genuinely independent of the particles being measured. But what if that's not true? What if the universe, from the very first instant of the Big Bang, wove together the hidden variables of every particle and the future choices of every experimenter who would ever test them, such that every Bell experiment, no matter how cleverly designed, is prearranged to look like a violation? To push this loophole back as far as possible, teams in Vienna and MIT pointed their random number generators at quasars, supermassive black hole engines so distant their light has traveled for billions of years. If the correlation between the photons and the quasar's ancient light was arranged to mislead them, it had to be arranged before the solar system was born. They ran the experiment. They violated Bell's inequality. Local realism must have either been wrong since the beginning of time, or it is simply wrong. Superdeterminism survives, technically, mathematically, as a loophole. But Bell himself noted, if we accept it, we must accept that the experimenter cannot independently choose their experiment. The hidden arrangement of the universe controls not just particles, but human choices, quasar colors, random number generators, and the thoughts of every scientist who ever tried to understand it. In a superdeterministic universe, there is no such thing as an independent test of anything. The scientific method ends. Then there's everything else. Most physicists look at that price tag and quietly close the door. So here is where we are. We know, with overwhelming, multiple independent experiment, Nobel Prize-level certainty, that the universe contains correlations between distant particles that cannot be explained by any locally realistic theory. Full stop. We do not know if reality doesn't exist until observed. We do not know whether there's a deeper non-local mechanism underneath. We do not know why Tsirelson's bound is exactly what it is. But I want you to sit with something beautiful for just a moment. Einstein called it spooky. He meant it as a criticism, a ghost in the machine, an embarrassment to clean classical thinking. But look at what the universe actually gave us. A connection that transcends space. A structure of correlation so delicate it can't carry a single classical bit of information, so it doesn't violate causality, but so real it can detect an eavesdropper on a satellite 1,000 kilometers up. A phenomenon so fundamental that without it, quantum computing is impossible. The universe didn't just ignore Einstein's demand for local realism, it built something better. Something stranger, something that required 80 years of the smartest humans who ever lived, arguing and experimenting and refusing to give up, to finally, definitively confirm. We are made of particles that were once entangled in the first seconds of the universe. The matter in your body and the matter at the edge of the observable cosmos share a history, woven before any star was born. Whether that connection persists, we can't say for sure, but the principle is real. The universe is not a collection of separate, isolated things. At its most fundamental level, it is one thing, and it remembers. If this video made you feel something, whether that's wonder, confusion, or the very specific satisfaction of having your brain slightly broken, hit the like button. That's all I ask. And I have a question for the comments that I genuinely don't know the answer to, and I mean that. If the universe has no objective facts independent of observers, what does that mean for the idea of scientific truth? Is science discovering a reality that's out there, or is it constructing a map of our interactions with something that doesn't fully exist until we interact with it? Leave your answer below. I read them all. If you haven't watched the episode 1 about spin yet, I would consider it the companion piece to this one. Same universe, different strangeness. Linked above. Subscribe, because that one changes everything again.